Hello, my name is Jordan Wu, and this is my Physics 2211 Lab 5, the falling slinky. The purpose of this experiment was to observe the motion of a slinky falling from a certain height and determine the effects of gravity and drag on the motion of the slinky. In particular, we observed the motion of the bottom point of the slinky. For this experiment, the key assumptions were that we set the center of mass at the bottom of the slinky, neglected the friction of the slinky, and neglected the distribution of mass in the slinky. The fundamental principles involved in this experiment was, to begin with, Newton's second law, or the momentum principle, which states that the net force on an object is equivalent to the change in momentum over the change in time. From this equation, we can derive the velocity update formula shown to the right, as well as the position update formula. Another fundamental principle involved in this experiment is the gravitational force near Earth's surface, which is negative mass times the gravitational constant g in the negative y direction. We derived the gravitational constant g by using the formula for the gravitational force, and it turns out to be around 9.8 meters per second squared. And this gravitational force points downward during free fall motion. Another fundamental principle involved is the drag force, which is the force opposite of the direction of motion due to air resistance. This is proportional to the square of the object's speed and points upward in free fall motion, as shown to the right. Here's a video of the tracker analysis that I found for this lab. Here is the glow script model, computational model that I used to model this experiment as well. These initial conditions were the system mass is around 0.015 kilograms with an initial position and velocity of 0. Change in time was said to be 1/60th, which is basically one frame. And our proportionality constant for the magnitude of drag force computed from guessing and checking was around 5.83. During these while loops, we can see that in this first section of the experiment, we calculated the gravitational force, which was the ball's mass times the gravitational constant in the negative y direction, and the tension force, which is opposite of the gravitational force but equal in magnitude. Therefore, the net force acting on this object is 0 at this time, and the position and velocity do not change in this first section. However, in the second section, we can see that the gravitational force is still there. However, now there is a drag force component, which is proportional to the square of the velocity of the ball, and therefore the ball will accelerate downwards and have that sort of motion. Here is the actual versus predicted motion of the spring slinky system. We can see here that the red represents the actual motion of the slinky, while the blue represents the predicted motion of the slinky, and both follow a very similar path. The similarities between these two graphs is both paths follow the same direction of motion in the same time interval. As in the first 5.7 seconds, there's no change in position, no change in velocity, because there is no net force acting on the object over that first few seconds. However, there is a lot more consistency in the actual motion, and this position fluctuates much more likely due to tracking issues or simulation errors. Some possible sources of error include inconsistent tracking of the bottom of the slinky, which could lead to minor fluctuations in position, as seen in the position versus time graph. Additionally, making assumptions and rough estimates of constants, such as the mass of the slinky and drag constant and the length of the height. These determine the motion and the resulting position of the model slinky, so it could actually be very far from an actual representation of ideal motion, as most of these constants were determined from guessing and checking to match the computational model with the actual model. Why does this happen? Why does the bottom of the slinky remain stationary? Well, this is because, as explained in the video, the tension force is equivalent to the gravitational force initially, as the bottom of the slinky stays there because the gravitational force is equivalent to the tension force, which are acting in opposite directions. However, therefore the bottom of the slinky is in static equilibrium, as the net force acting on it is equal to 0. Then, when the slinky collapses, there is only gravitational force and drag force acting on the slinky, meaning it will accelerate downward.